How does variational inference work in VAEs? Imagine trying to understand a complex shape hidden inside a box. You can't see it directly, but you want to guess what it looks like. That's similar to what variational autoencoders do with data. They try to learn the underlying structure of data by creating a smooth, flexible map of all possible data points. Now, to do this, they need to figure out the best way to describe this hidden shape, which is tricky because the true description is often too complicated to calculate directly. This is where variational inference comes in. It helps VAs find a good enough approximation of this hidden shape without doing impossible calculations. The process starts with an encoder network. Think of it as a translator that takes your data, like an image or a sound, and turns it into a set of numbers that describe a probability distribution. Usually, this distribution is a Gaussian, which looks like a bell curve, and it's defined by a mean and a variance. These numbers tell us where the data likely sits in the hidden space and how spread out it is. This distribution is called the approximate posterior because it tries to mimic the true but hard-to-calculate posterior distribution of the data. Next, the goal is to make this approximate posterior as close as possible to the real one. To do this, VAs maximize something called the evidence lower bound, or ELBO. Think of the ELBO as a score that combines two things. The first part is how well the decoder can recreate the original data from samples drawn from the approximate distribution. If the decoder can produce realistic data, the score goes up. The second part measures how close the approximate distribution is to a prior, usually a simple normal distribution. This step keeps the latent space organized and prevents it from becoming chaotic. A key trick used in VAs is called the reparameterization trick. Instead of directly sampling from the approximate distribution, which would make it hard to calculate gradients needed for learning, the model samples from a fixed noise source like random static. Then it transforms this noise using the learned mean and variance. This way, the model can still learn through gradient descent because the sampling process becomes differentiable. By combining these steps, VAs learn a continuous and meaningful latent space that captures the essence of the data. This space allows the model to generate new data points that look similar to the original data, like creating new images or sounds. Unlike traditional autoencoders that just compress data into fixed points, VAs understand the data's underlying probability structure, making them powerful tools in generative AI. They are used in many areas, from creating realistic images to detecting anomalies or filling in missing data. Understanding how variational inference works helps us see how deep learning models can learn complex patterns and generate new content responsibly.